The infrared half wave is a simple and easy to use antenna, but the way you deploy it can completely change its performance. In this video, I'm going to take a look at the most common configurations and compare the radiation patterns to see which setup makes the most sense depending on your goals. In my last video, I go over the basics of an end-fed half wave, and I built a simple but efficient 49:1 unit. In this one, I'm going to take it a step further and look at the different ways to deploy this antenna. That's one of the great things about an end-fed. You have a lot of flexibility in how to use it. It's resonant on multiple bands, and the radiation patterns actually change not only with each configuration, but on each band. So I thought it'd be really interesting to take a look at the computer modeling and try to get an idea of how I want to use this antenna in the future. End-fed half waves get a little bit of hate, and I understand why. They're not the most efficient antenna. In fact, a while back I was doing a Parks on the Air activation, and I had a toroid in a 49:1 unit get so hot that it almost melted through an enclosure. But every antenna is a compromise. The end-fed half wave trades a bit of efficiency for convenience, multiband coverage, and flexible deployment. So depending on your goals, that trade-off may be worth it. Lately, I wanted to give this antenna another shot, especially since I built one of these, which is an efficient 49:1 unit. When I first started using end-fed half waves, I never really paid attention to how I put them up. I would just deploy them in the most convenient way possible, and they worked okay. But lately, I've been using more directional antennas and trying to get my signal to more populated areas in hopes of making more contacts. So I live in Texas, and so a lot of times I'll point my antenna northeast, and that helps me make contacts in the Midwest, along the East Coast, and then Europe if conditions allow. The end-fed half wave is a very versatile antenna. You can set it up in ways where you get a low takeoff angle and a little bit of gain, or as more of an INVIS style antenna. So understanding each configuration can help you match the antenna to your goals, whether that's making a bunch of regional contacts or trying to get a little bit of DX. Before we get into the common configurations, I wanted to point one thing out. An end-fed half wave has the same current distribution along the wire as a dipole. So if you deploy them in the same way, it's going to have very similar radiation patterns. The only real difference is how we match it at the feed point. So, for example, here is a 20-meter end-fed half wave up 33 feet horizontally, or a half wavelength. The radiation patterns are basically identical to a dipole. The first configuration I want to take a look at is a vertical end-fed half wave. Now, a 40-meter vertical end-fed half wave is not realistic for most people. However, they're commonly used from 20 meters to 10 meters, and they have a couple advantages over a quarter wave vertical. First of all, a lower takeoff angle, a little bit more gain, about a dB or so, and then you also don't need an extensive ground plane like you do with a quarter wave. Because this is a voltage-fed antenna, the return current is much less, so you just need a short counterpoise, approximately 5% of a wavelength on the lowest frequency. So here I have ANA Gal Basic pulled up, which is a fairly easy to use antenna modeling software. And I have a vertical piece of wire that's approximately 33 feet long, and then a short counterpoise with a feed point at the bottom. And in the setup, I have the feed point impedance at 2,450 ohms because we're using that 49:1 unit. So on 20 meters, you're going to notice that this is a very common omnidirectional pattern with a low takeoff angle. As you can see, the max gain is at 18 degrees and it's 0.8 dB. And then at 10 degrees, we're at negative 0.9, so about -1. And then 5 degrees, we're at negative 4.6. Now, this is actually not a straight omnidirectional pattern. If you notice, down here, we're only getting 0.3 dB. You get a little bit more gain in the opposite direction of the counterpoise. So I have the counterpoise running in this direction, and in the opposite direction, you'll see that's where we get the max gain. So It's not a huge amount, but you do get slightly more gain in the opposite direction of the counterpoise. Now let's compare this to a quarter wave vertical. So let's pull up a quarter wave vertical, and you'll notice that the half wave is in black and the quarter wave is in red, and you get slightly lower takeoff angle with the half wave and a little bit more gain. Now, is this going to be noticeable in the real world situation? It's hard to say, but in theory, the half wave is better. A 20 meter infed half wave will also work on 10 meters. Now, as you can see here, the angle of radiation is much higher, so it's not quite as good. So not the best for DX. As you can see from the 3D model here, you get much more high angle radiation than with the 20 meter infed half wave. It'll work, but it's probably not going to be the best. The next configuration I want to take a look at is this sloper, which is probably the most common configuration. Here we have a single radiating element. It's approximately 66 feet long, and it's 33 feet high at the end. And then I've got a short counterpoise with the feed point approximately 3 feet off the ground. So on 40 meters, this is going to be a Invis style antenna. Most of your radiation is going straight up, but you get a little bit more gain towards the feed point. So the wire is sloping in the y-axis, and you can see this a little bit better in the 3D model here. So as you can see here, this blue line is our antenna, and you get a little bit more gain towards this way, but it's mostly an Invis style antenna. So let's take a look at 20 meters. So as you can see here, we're starting to get more lobes, and on the 3D model you can kind of see what's going on. So this is a full wavelength antenna on 20 meters. So we have two main lobes. We get a little bit of a lobe at lower angles towards the feed point and the counterpoise, and then we get this kind of horseshoe shaped lobe with fairly high angle of radiation towards the direction of the sloping wire. So right here, our max gain is approximately 45 degrees off each side of the wire, and it's 4.6 dB at approximately 36 degrees elevation. This right here is not really helpful because it's just taking a slice looking across this direction. So our gain is not across the x-axis, so this isn't really going to be super helpful to see where our gain is going and what elevation. But what we can do is we can change our elevation here, and this is 5 degrees. You can see we're -6 off of these two lobes, and then -4.5 off the back. And then at 10 degrees, you can see we're -1 off the corners, and then -0.5 off the back. And then at 15 degrees, we're about 1.4 off of these and 1.4 off the back. And then finally at 20 degrees, you can see we're starting to get some decent gain, almost 3 dB off of the corners, and then the back approximately 2 to 2.5. So on 20 meters, it's not the best, but you do get a little bit of gain off the back ends and then off the front corners. So let's take a look at 15 meters. And it's very similar to 20 meters. If we look at the 3D model, you'll see that since this is the third harmonic, you get another lobe. So we get a little bit of broadside gain, but we get a little bit lower angles on these front lobes and then on the back as well. So we can see here we're now at 5.3 dB at 22 degrees, which is fairly good. And then we can take a look at 5 degrees. we're negative 2.4 on the front and about negative 1.5 on the back. At 10 degrees, 2.2 on the front corners, and then 2.5 to 2.2 on the back. And then at 15 degrees, we're about 4.2 dB on the front corners, and then about the same on the back. So kind of the back corners have the most, and then straight back you get 3.4. And then on the sides you get a little bit. And then finally, let's take a look at 20 degrees. 5.2 dB off the corners and 4.5 off the back. And then broadside, you get a little bit. So it's not terrible on 15 meters, looks pretty good. All right, so let's take a look at 10 meters. So 10 meters, we get an additional lobe, and we still get these kind of low angle corner lobes and a little bit off the back. So kind of similar to 15 meters, but we also get a lot of high angle radiation off the other lobes. So it gets a little bit more erratic as we go up in frequency. So if you can see here, 5 degrees, we're at negative 0.4 and negative 0.5 off the back. At 10 degrees, we're getting some pretty decent gain, 3.8 off the front and 3.4 to 2.5 off the back. And we get a little bit of on these broadside lobes. And then at 15 degrees, 5.2, and then off the back 4.4 to 3.5, and then just a little bit off the broadside. Finally, let's take a look at 20 degrees. We're getting 5.4 dB and then about 4 off the backside. So not terrible on 10 meters. The next configuration I want to take a look at is the inverted V, which is another common configuration. As you can see here, I've got the inverted V. The feed point's still up about 3 feet, and then it goes up to 30 feet in the middle, and then down. And the middle is right in the middle of the antenna. And so first we're going to take a look at 40 meters, which is going to be just the Invis style antenna that we've seen before. So nothing really special there. This antenna actually looks really good on 20 meters. So we get some really nice low angle gain on 20 meters. So if you can see here, our max gain is at 18 degrees, and we get 3.4 dB at 18 degrees. And then let's take a look at 5 degrees, we're approximately -2, and then 10, we're 1.7 dB. And as you can see, it's a nice broadside gain. So really looks quite good on 20 meters. Let's take a look at the 3D model here. So as you can see, the wire's going this way, and we get these really nice broad lobes on the broad side of the antenna. So really looking good on 20 meters, and we can compare that to a halfway vertical. So let's take a look. So as you can see here, the inverted V has more gain and lower takeoff than the halfway vertical. So on 20 meters, this looks really good. The problem is when we go up to 15 meters, things get really kind of wonky on 15 meters with the inverted V. And so let's look at the 3D model so you can kind of see what's going on. So almost everything is going straight up, and you get kind of these weak lobes off the corners in a clover shape. So really not great on 15 meters. Let's see here. Let's just take a look at 10 degrees, 0.8 off of this corner. And let's take a look at 15 degrees, 2.1, and then at 20 degrees, 2.3. So you get a little bit of gain off the corners, but most of the radiation is going straight up on 15 meters. So not an ideal antenna on 15 meters in my opinion. And then on 10 meters, let's take a look at the 3D model, kind of see what's going on. So you do get some really low angle gain off the corners again, but mostly the biggest lobe is going kind of really high. So let's take a look at those low angles. Let's take a look at 5 degrees. So you're getting, 0.6 dB off the front or towards the wire. So the inverted V feed point's here and it's going in this direction. And then off the back, negative 0.1. So that's at 5 degrees. And then at 10 degrees, we're getting 3.8 dB. So it's not bad on 10 meters. And then let's take a look at 15 degrees. About 4 dB on the front, and then the back corner is 2 dB. So it's not terrible on 10 meters, but 15 meters, the inverted V didn't look very good. Okay, the next configuration I'm going to take a look at is the inverted L. So as you can see here, I've got a wire running up, so I plan on using my 31 foot mast and then just having a horizontal wire going away from that, and probably supported either with a tree or another mast. And then I've got the feed point about 3 feet up, and then the short counterpoise. So first of all, let's take a look at 40 meters. So as you notice, this is very similar to the other configurations, basically an invis. However, what you will notice is it's kind of squashed down a little bit. And I think it's because we have that short vertical section of wire. So we get a little bit of gain at lower angles compared to the other configurations. And we can actually compare the far field plots of the other antennas. Here's the sloper in red, and then we will add the inverted V. So as you can see here, the inverted L is in black. You get a little bit more gain at low angles. However, it's still mostly an invis antenna, and I don't think you're really going to notice a huge difference on 40 meters. Now let's take a look at 20 meters. What you're going to notice is we get some pretty decent broadside gain. So remember the wire's running in this direction, the inverted L section. And so really nice broadside gain and fairly good takeoff angle. So I think our max gain is at 24 degrees and it's 4.6 dB. And then we'll look at 5 degrees here, which is around negative 3.7, and then 10 degrees we're getting 0.8. So looks pretty good. Let's compare that briefly to the inverted V, which looked really good on 20 meters. Here we go. So as you can see, the inverted V has slightly lower takeoff angle, but the inverted L has overall more gain. So inverted L looks pretty good. Let's take a look at 15 meters. And if you remember, 15 meters did not look great on the inverted V. We got a lot of high angle radiation. Let's take a look at the 3D model first to kind of see what's going on. So as you can see, a clover leaf shape here with all 4 corners having a little bit of gain. More off the corners of the horizontal section of wire. So let's take a look. Right here, our max gain is 5.8 dB at 25 degrees. So let's drop this down to 5 degrees. And we've got negative 1.5 off the front corner and negative 3.4 off the back corner. At 10 degrees, we've got 3.2 off the front corner and 1.5 off the back. And then at 15 degrees, 5.3 and then 3.6 off the back corner. And then at 20 degrees, we've got 6 dB off the front corner and 4.4 off the back corner. So on 15 meters, the inverted L looks pretty good. Let's take a look at 10 meters. So let's take a look at the 3D model first to kind of get an idea of what's going on. So kind of similar. We get the two lobes off the front corner, and then we get kind of a higher angle lobe off the back. So let's take a look at 5 degrees here. Negative 1.6 and negative 4.1. At 10 degrees, we're starting to get some decent gain, 3.1 dB off the front corner, and then 0.7 off the back corners. And then at 15 degrees, 4.7 and 2.6. And then at 20 degrees, getting almost 5 dB off the front, and then about 3 off the back corners. So not too bad on 10 meters. Okay, that was a lot of information. So I figured I would summarize each band and what I thought about each configuration. So on 40 meters, they were all pretty similar. The inverted L had slightly lower angle gain, so it was a little better, but they were mostly Invis style antennas on 40 meters. On 20 meters, the inverted V looked really good. It had low angle gain, broadside to the antenna, but the inverted L had more gain, just slightly higher. So both the inverted V and inverted L looked really good. If I was only going to work 20 meters, I might pick the inverted V. Now on 15 meters, the inverted V didn't look very good to me. The inverted L and the sloper both looked pretty good, so I would probably go with the inverted L on 15 meters. Now on 10 meters, it was kind of similar. Both the inverted L, the sloper looked pretty good. So overall, I think the inverted L looked the best, and that's probably going to be the one that I try when I get out to the park. But I have to decide how I want to deploy it and which direction I'm going to put that horizontal portion of the wire. And looking at the azimuth map, if I put the antenna directly north, that should give me nice broadside gain and cover most of the US. I'll have a little bit of nulls on the north and south, but I should be able to get most of the states. I could even slightly point the antenna northwest if I wanted to get to the Midwest and avoid that nulls there, but I think mostly north will do pretty well. Now on 15 and 10 meters, most of the gain was 45 degrees off the end of that horizontal section of wire. So if I have the antenna facing directly north, I should be able to get into Europe if the bands are open on 10 and 15 meters. And then late in the afternoon, it might be possible to get to Japan. But that's all due to band conditions, and there are a lot of variables. But I think that's the way I'll deploy this antenna. Hopefully you found this video interesting. In my next video, I'm looking forward to taking this antenna out to the park and setting it up and trying to make some contacts. Until then, 73.